These are Mrs. Mooney's notes for Chapter 15, Wave Interference and Diffraction. By the end of this chapter, you should be able to explain how light waves interfere with one another to produce bright and dark bands, and to explain why interference and diffraction provides evidence for the wave nature of light. What do you think? You have learned that sound waves and water waves can interfere both constructively and destructively. Can light waves interfere as well in the same manner? If you answered yes, you answered correctly. Light waves can interfere both constructively and destructively. In the example shown below, the two waves here, the first and the second wave, are meeting in phase, so constructively interfere and producing amplitudes that add, and this would show up as brighter light. In the second example here, the two waves, the first wave and the second wave, meet out of phase, so the amplitudes would subtract, which is destructive interference, and this would result in a darker or dimmer light. A light source with a single wavelength, which would be a single color, is called monochromatic. Mono refers to single, chromatic refers to color, so monochromatic light would be light of a single color. If monochromatic light interferes constructively, the wave would have the same wavelength and color, but the wave would have a greater amplitude, and this would show up as a bright spot. If monochromatic light interferes destructively, the resultant wave would have the same wavelength and color, but would have a smaller amplitude, and this would show up as a dark spot. So in the two examples shown here below, the bright bands is the result of monochromatic light interfering constructively. Red light in this example and blue light in this example. And the darker bands is the result of the monochromatic light interfering destructively. In order for two waves to produce a stable interference pattern, such as the two examples in the previous slide, the phase of the individual waves must remain unchanged relative to one another. In Figure A, the two waves are in phase, meaning trough is in line with troughs, and the crests are in line with the crests. In Figure B, these two waves are out of phase, meaning one crest is in line with the other's trough, and the first one's trough is aligned with the second one's crest. So this is out of phase versus in phase. Coherence is when the phase difference between the two waves is constant. In other words, for this example, the waves would always stay in phase, or the waves would always stay out of phase. And in order to get a stable interference pattern, this must remain true. In order for interference to occur, waves must maintain a constant phase relationship, or in other words, must be coherent. So that the waves that are in phase must stay in phase, or if the waves are out of phase, they have to stay out of phase. In order for interference to occur, the light has to be coherent. Incoherent light has phase relationships that shift. Sometimes the light may be in phase, other times the light waves are out of phase, and if that's the case, then interference will not occur. So incoherent light does not produce interference patterns. The light must be coherent in order to produce an interference. An interesting example of light waves interfering can be observed in soap bubbles or thin film of oil on water. The colors observed are not the result of the separation of white light, such as done by a prism, but is the result of light waves interfering constructively and destructively in the thin film of oil or the thin film of the soap bubble. An English physician, Thomas Young, attempted to prove that light had wave properties when he produced an interference pattern by shining light from a single coherent source through two slits, and he saw the resulting interference pattern. He presented his findings in 1803, but was ridiculed by the scientific community. His conclusions did not gain acceptance until around 1820, when a noted French engineer and physicist Mr. Jean Fresnel proposed a mathematical solution for the wave nature of light in a competition. And an interesting note on Mr. Fresnel, not only was he a noted engineer and physicist, but he was also a lens maker and invented the Fresnel lens, a lens that is used in many lighthouses, including our very own Jupiter Lighthouse. Diffraction is a change in direction, or the bending, of light waves as the waves go around an obstacle or through tiny openings. Diffracted light can also produce an interference pattern of bright and dark bands. Diffraction gratings are devices made up of many tiny slits spaced very closely together, and when monochromatic light is passed through a diffraction grating, it produces an interference pattern of bands of bright and dark fringes. When white light is passed through a diffraction grating, it produces a full spectrum of color, very similar to what you might see in a reflection off a CD compact disc surface. There are many practical applications of diffraction gratings. Diffraction gratings are used in spectrometers to separate light into its component colors. Diffraction gratings are used to study the composition of distant stars, and this was how helium was first observed on the Sun and later discovered on Earth. The fact that light waves can interfere to produce resultant waves that are either brighter or less bright than the component waves provides strong evidence for the wave nature of light. Light bulbs emit light of many different wavelengths and thus emit incoherent light. Lasers, on the other hand, produce a narrow beam of coherent light. LASER is an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. Lasers use light, electrical energy, or chemical energy to produce monochromatic, coherent light. There are many important applications of lasers. Lasers are often used to measure distance. Lasers can measure distance very accurately because the beam does not spread out very much. Also, there are many very important uses of lasers in the medical field, such as the ones listed below.